We're slowly getting our technical kinks out, but you all can see that we are joined by Heather Cegla and Emily Rickman. And in a second, everyone in the classroom will get to see you too. So bear with us while we take our extra minute to get there.
Let me see.
Yeah, that's
No,
great.
this was not good. Oh, it's here now. Okay.
I think you can just exit full screen view.
Yeah. Second. Yes. You know what to? We need.
I think this is good because then I can go my screen and webinar.
Yeah, and I think we can drag this over.
Okay.
Is that okay?
Yep, that's fine. So let's just drag it over.
Yes.
Right.
Yes.
Yeah.
And then the people in the room are gonna see that too.
Yeah, that's fine because I'm gonna stop screen sharing in just a minute.
Yes.
Yeah, that's fine.
Yeah. Yeah.
Now my clicker doesn't work. All right. Can everybody out there hear and see us? So Heather, you can turn your video back on too whenever you're ready. So my name, I realize I forgot to introduce myself. So I'm Anjali Tripathi. I work at NASA's Jet Propulsion Laboratory. I will hide in camera view for a second. It's fun to be in the back. As a short person, this is a new experience for me that I've never gotten to experience. So I'm delighted to be NASA's Exoplanet Science Ambassador, which means I get to engage the community, both other scientists and the public. And it's my great pleasure to introduce our panelists today. So we are joined by two folks who are on other time zones. And let's see. So I'm just going to go through this in the order that the slides are in, and then I will bring back the folks who are remote. So in the middle here in person, we have Chaz Beichman, who is the executive director of NASA's Exoplanet Science Institute. So this slide just gives you a little bit of a bird's eye view of people's career trajectories. Chaz, you've done so much that I had to condense a lot of things together. All of you are like, oh gosh, what did she say about me? But anyway, so Chaz has a storied career here at Caltech and JPL, and he has this great perspective on some of the missions that have happened in the past and where we are now. Then I will come back to Heather and Emily in just a second. Next to Chaz, we have Stephen Kane, who's a professor of planetary astrophysics at UC Riverside. Stephen used to be here actually at NExScI, but he's done a lot of other things in between. And he originally hails from Australia. And so, he's someone who was chosen to be here with us today. And he can tell you a little bit about that perspective, and especially the interplay between astronomy and planetary science, which is something that I think not all of us think about every day, especially when we have planets that are so similar to Earth just in our own backyard. To Chaz's right, we have Jessica Spake, who is down the road at Carnegie Observatories as a staff scientist. Jessica also used to be here at Caltech as a Sagan Fellow and 51 Peg B Fellow. And she can give you that perspective also on coming to the US and choosing to be here and work somewhere that's privately funded. I will now go online to Heather and Emily. So we have Heather Cegla, who's at the University of Warwick. She's an associate professor there and also a UKRI Future Leader Fellow. One really interesting thing about Heather is she has all kinds of experience in Geneva and working on KEOPS. And she can give you this amazing perspective on what it's like to collaborate in some of these European missions and what that interplay looks like in the UK. And Heather, unlike, Jessica sort of did the reverse direction. She was from the US, or not was, you are from the US and moved over to the other side of the pond. So she can tell us about what that transition looks like for those of you who might be thinking about possibilities out there. And then finally, we have Emily Rickman, who's currently on the other side of the country, who is the European Space Agency astronomer at the Space Telescope Science Institute, which is on the campus of Johns Hopkins. Emily was a student in the UK and then also went over to Geneva and is now employed by the European Space Agency, but based here in America. So you can see we've got a great panel offering us some perspective on what it looks like to work on some of these topics. So Everyone, bear with me while I struggle with Zoom. Half a second more for the people in the classroom. Okay, and let's see. Stephen, we'll come back to your slides later if that's okay. All right, and let's see if I've broken everything. Online, I think you all can see our delightful remote panelists, and in the room, we can see you. So with that, I'm going to offer you all a microphone that you get to share. And I'm going to just ask that our remote folks jump in whenever the mood so strikes your fancy. And maybe we can just go in a line question, which is, can you tell us a little bit about how you got into exoplanets? Because I think exoplanets is such a recent field. Everyone has a different journey in it. So what was the field like and your journey into it at that time?
How short? Keep this. I just cover set of this. Okay. Hi, I'm Jessica. I'm from the UK. I was an undergrad doing a year abroad in Europe. I spent a year in France actually during my undergrad. I was extremely depressed. I was a very bad student. I was really struggling with classes, and I managed to drag myself to one astrophysics class. And in it, the professor said, "Here is how you discover exoplanets." And he explained the transit method and the radial velocity method. And I was like, "Exo what?" I'd like never heard of an exoplanet before. This is back in 2012, so a little while ago. I didn't know that we had found them. I thought these discovery techniques were very elegant. I was very proud of humans for figuring out these like neat tricks to finding them. And my world like suddenly expanded. And from that, during that class, I was like, I don't care what it takes. This is the coolest thing I've ever heard of. Yeah, I'm going to do everything I can to like do this for a long time.
Yeah, when I started out, I was actually interested in finding what we now call protostars. We were just developing the techniques in infrared astronomy to start looking for stars as they formed out of molecular gas and dust. We started out being able to find O and B stars, and that was nice, but not much to do with stars like our own sun. As we developed better techniques and moved into space, we were able to detect suns that were much more like our own sun for solar type stars, and that's with the IRAS satellite. Then IRAS made one amazing discovery, which was main sequence stars like our sun, mature ones, not protostars, were surrounded by disks of orbiting material, so-called debris disks. And that was first found by their infrared excess. And then within a year or so, Rich Terrell and Brad Smith made a coronagraphic observation, very crude by today's standards, maybe a rejection of 10 to the minus 3 or something, but at visible wavelength, and saw that the star Beta Pictoris had an edge-on disk of material that looked like everything you'd expect from a dusty solar system seen edge-on. It'd be a long time before anyone found that there was a planet embedded in that system. But that was definitely putting us on the path to going from stars like our own sun to solar systems like our own solar system to eventually getting to all the planets we've now seen today with some of the techniques that Jessica mentioned, plus a whole suite of other ones. So that was sort of the start, and the story goes on.
And just a quick question, Chaz, what year was that?
Excuse me?
What year was that?
So IRAS was 1983. So the infrared excesses were found around some of the brightest nearby stars by IRAS. And then within a year or so, the first edge-on image of a solar system was made of Beta Pic, but it was then quite a few years later before the first exoplanets were themselves discovered.
Hello, everyone. I'm from Outback Australia originally, and I grew up in a very fiercely working class family and extended family. Suffice it to say, they disapproved of my decision to go to college. I'm a first-gen college student. And I grew up very interested in planetary science, sitting in Outback Australia, glued to the TV, watching the images from JPL of the Voyager 2 flybys of Uranus and Neptune, that sort of thing. And I was fascinated by Venus, and I intended to go into planetary science. I got a lot of advice in the mid 90s when I finished undergrad about what I should do next. And I spoke to somebody named Vicky Meadows, who had also been Australian, left Australia to come to JPL to study Venus. So I really wanted to follow that path. And at that same time, exoplanets were being discovered. And in particular, 51 Peg at the end of 95, when I finished undergrad, caused the emergence of opportunities to actually do a graduate degree in exoplanets, which was very much emerging at that time. So I went that pathway. Vicky encouraged me to go that way because she could see it was expanding rapidly. So I started out microlensing. Then, as you saw in my bio, I did a couple of postdocs, which exposed me to things like transits, radio velocities, imaging. But about 15 years ago, I returned to my first love, which was planetary science and studying Venus and putting these two fields together, which is very much needed. And so I'm now on the science team for the NASA Da Vinci mission, and excited to be going back to Venus and applying everything there to exoplanets.
That's awesome. Heather, let's go to you.
Yeah, thanks for inviting me to join you all. It's a shame I can't see everyone, but at least I can see the other panelists. So that's nice. I got involved in exoplanets because I did my undergrad in physics and I knew I wanted to do astronomy and I knew I wanted to do research. And the first summer research undergraduate experience that I did, so an REU program, was back at the University of North Dakota, and we were doing photometric follow-up of radio velocity detected exoplanets. So we were trying to see if they transited. And so we were just doing this with like a small, I think maybe 10-inch telescope or something. And essentially we were kind of just sat in a field in North Dakota getting bit by mosquitoes, trying to see if this planet might transit. But I enjoyed it enough to stick with it. I did a few other internships and then ultimately came back to exoplanets because especially the ones that transit are you can just get so much information if you have the photometry of the transit and you have the radio velocity of the follow-up, and being able to confirm and characterize planets to such exquisite detail with just those sets of measurements was pretty interesting. So that's kind of how I got into the field.
Thanks, Heather. Over to you, Emily.
Yeah, hi everyone. Thanks for having me on the panel today. So yeah, I think my first exposure was I did this second year course during undergrad when I was in Sheffield by Professor Simon Goodwin on this course, like how to find aliens or name something like that. And I was like, well, that sounds fun. And then I learned about all of these different techniques of how we find planets beyond our own solar system. And I just got really excited about that. And then I spent 1 year studying in Australia at the Australian National University. And I was working at Mount Stromlo there. So there's a observatory there. And I was then doing radial velocity follow-up of transiting exoplanets from Kepler K2. So this was back in like 2014. And we thought that we had like found a planet. It turned out not to be, but it was like a very exciting time to be like an undergraduate student and potentially finding your first exoplanet. And then it kind of kickstarted from there for me. And then I ended up studying my PhD in Geneva, just kind of like the home of the founding fathers of exoplanets in a way. And so Heather and I actually overlapped for the time that I was there. And yeah, never kind of looked back, but I ended up transitioning more into direct imaging and direct spectroscopy of exoplanets, which is what I do now.
So you all have stories of exoplanets that go back decades and recently, and we don't seem to have run out of things to do, which is good. And so I'm curious for the room, you all do so much. We don't have time to go into detail about all of your work. But just to give us a little snapshot into your worlds, what is the question that you're working on right now that most excites you, right? And you can talk about the unanswered bits or the parts that you've answered. But I think before we sort of go into the nitty-gritty logistics of doing it, it'd be great to have this big picture sense of what you do. So, who would like to start?
Well, right now we're in the midst of submitting a couple of papers describing our work with the James Webb Space Telescope, trying to identify an exoplanet orbiting our closest solar twin, Alpha Centauri. And those papers will go in the next day or two. And the data, we'll have a press release that on August 7th. So stay tuned and you'll find out whether Alpha Cen A has a planet orbiting it or not.
Will we be visiting it, Chaz? Will we be visiting it anytime soon if it exists?
We'll see what happens.
Thanks. Most of my work focuses on exoplanet atmospheres, and I'm really interested in mass loss. So one of the main questions unanswered today is, what kind of planets can hold on to atmospheres long enough for life to evolve on them? So that's what I spend most of my day-to-day research time. But I'm definitely feel like I like to leave some of it for surprises. I feel like I'm very inspired by new techniques that are popping up everywhere, new instruments, new directions. So there's definitely I like to keep a lookout for the surprising ones that aren't driven by direct research questions.
So as I mentioned, I study Venus, and a big part of the reason I do that is because what's central to my research is planetary habitability. What drives a planet to be able to sustain long-term temperate surface conditions? And so Venus is sometimes unfairly referred to as Earth's evil twin. By the way, if any of you ever want to see an Earth-sized planet, get up at 5 a.m., look and look to the east. It's currently the morning star, and it turned out completely different from Earth. And previously we thought we knew why. Well, it's 30% closer to the sun, receives twice the amount of flux. That's it, job done. But now in the past decade or two, with more advanced climate models where we can actually start to assess the energy balance at planetary surfaces as a function of not just their proximity to their star, but also in terms of things like their obliquity rotation rate, the topography on the surface, we find that the situation is far more complicated. And so with Venus, there is very good evidence that it did have oceans in the past and lost them. And that's one of the big outstanding questions that not only applies to the Earth-Venus dichotomy, but obviously is enormously important for our ability to infer the surface conditions of exoplanets, which is what many of us ultimately would like to do.
Thanks, Stephen. Over to you, Emily.
Yeah, so I'm also focusing a lot on exoplanetary atmospheres, but doing this directly. So historically, most atmospheric observations have been through the transit method, which is really powerful. But thanks to the James Webb Space Telescope, we're able to really probe atmospheres directly for the first time at moderate resolution. So I'm leading a JWST program at the moment where we're looking at a number of different companions which have well-constrained dynamical masses. So that means that we have their masses measured through other techniques like radial velocity and astrometry. And then we also have archival atmospheric data from ground-based instrumentation, and then we're combining that with longer wavelengths that we're able to access thanks to JWST. And so we're trying to understand what we're seeing in these different objects. And a couple of weeks ago, we just had a press release from a postdoc that's working with me, Keelan Hoke, that led a Nature paper on the first silicate direct detection in a multi-planet system. And so I think this is really opening up a new avenue to understanding directly what we're seeing on these giant, widely separated planets that are similar to Jupiter and Saturn, etc., in our own solar system. So I care about things that are typically quite widely separated away from their star.
Great. And Heather.
Yeah, so my background is in the radial velocity conformation and characterization of exoplanets, both from an observation point of view and a simulation point of view. And so with one hat, I wear the co-lead to the Extreme Precision Radio Velocity Research Coordination Network. So alongside Jen Burt, I'm interested in trying to corral a bunch of astronomers across the world to see if we can push that endeavor further. The biggest stumbling block there is the stellar variability. So the fact that the surface of our sun is not homogeneous and evolves over time, that is big enough imprint in our data to completely mask an Earth analog. And so as we try to push closer to try to confirm Earth twins, especially for the next set of space-based missions like the Habitable World Observatory that will be trying to probe the atmospheres of those planets, we need to find them first and to characterize their masses and everything. And so we need to understand the star a bit more. And my student Ginger Frame has a paper out using 3D magnetohydrodynamic simulations to do this and extending that work. And then my postdoc, Sis Laji, is taking that and extending it towards a larger chunks of wavelength. And then Vatso Panwan and my group as well is starting to look at how the variability of the star can also contaminate our characterizations of the exoplanet atmospheres. And a lot of that work historically in the past has been done in low resolution, but Vatso is working in high resolution. And then one other area of interest is if the planet happens to transit the star, then we can use the planet to probe and spatially resolve the star and look at the star, like by watching the star when it's by itself. And then when the planet goes in front, we subtract those two observations, and then we can look at the local patch of the starlight along the transit chord. And Vedad Kunovak, who works with me but is an independent Newton fellow, is working on a really interesting set of data of WASP 85A, where we see some evidence where the planet occults a star spot. And he's starting to probe the local star spot on a star other than the sun for the first time, which is really cool.
Thanks, Heather. So it sounds like there are lots of interesting questions from both within our backyard to distant atmospheres. And so there are lots of questions, lots of people interested at different stages. But if you're interested, where do you go to do this work, right? Because it can seem like quite a barrier from going from the outback to being at a university. And so given that you all represent very different institutions, right? We have private funding for the Carnegie observatories, we have a science center, we have a public university in America, we've got, European funding at another science center and a university in the UK. I was wondering if you each could share a little bit about your institution, right? How do people end up there? What sort of opportunities and unique aspects are there that make it different from the academic setting that people are used to as a student? Who would like to go first? I don't want our remote friends to feel like they are second class. So I will take volunteers if whoever would like to speak first.
I mean, I'm happy to jump in because I think, so I'm based at the Space Telescope Science Institute. So I think it's actually quite a unique setting. And so we basically operate space telescopes. So that's the Hubble Space Telescope, the James Webb Space Telescope, and the soon to be launched Roman Space Telescope. And so there are different aspects of operating these missions. There's both the science operations and the missions operations. And so we focus a lot on the science operations side. And what that basically means is we take data from these telescopes and we do like calibration programs. So like the data you would take for like a science program, we analyze it in a similar way to make sure the instruments are behaving as anticipated or they do slowly degrade over time. So like taking into account how the instruments might change and accounting for any like obscure behavior so we can have the data products available to the community that uses these different space telescopes. We have a very large archive of all of that data that we're here to like help with and make available to the people that use it. So we do things like user support as well. So if you ever in the future work on a program with one of these telescopes, you can provide a help desk ticket to us and we can try and answer your questions because we are supposedly the experts in dealing with this data. So we might be able to account for obscurities that happen and help out with those. Things like documentation as well, like the data handbooks and the instrument handbooks that come from these telescopes so that astronomers can propose for these to get data with these telescopes and to use that data. So yeah, there's many different aspects to what we do. And so for my particular job, so I spend 50% of my time doing independent research, and I can sort of choose to do whatever I want with that 50% of my time, and the research that I spoke about in exoplanet atmospheres. And then the other 50% of my time I spend supporting science operations for Hubble and James Webb. And so the people that come to Space Telescope, we have students who are affiliated with us through Johns Hopkins University because we are on that campus. So we do have some undergrads and graduate students that work with us and do projects with us. And then we do have postdocs, and we have a fair number of fellows and fellowships available every year that people can apply for and come and work on some of the research that we're doing. But the staff positions, like what I'm doing, typically look something like a 50-50 split of doing research and doing operations support. And we're a mix of space agencies, so we're predominantly funded through NASA, but we also have people like myself who work for the European Space Agency and some people who work for the Canadian Space Agency. And that's because our big space telescopes are partnership missions. So we have people that represent all of those different space agencies to work together. Yeah, so it's like a slightly different aspect to academia. It's more like operations focused, but still getting the opportunity to work in research as well.
Thanks, Emily. And actually, then I'm going to go to Chaz next because you're also at a similar sort of institution. Is that right?
What Emily said. Except our focus is on, supporting at the NExScI NASA Exoplanet Science Institute. Our focus is less on operating missions, but rather gathering the data from the various missions. We run the NASA Exoplanet Archive, the follow-up program website. We're closely involved in some cases with running the U.S. arm of various European missions, such as the upcoming Ariel mission. We also do a lot of work for operations of the Keck telescope and also the NEWIT RV telescope. But basically, the functions that Emily described are basically mapped into the projects for which we have responsibility: operations, science. But in every case, there's a scientist and an engineer working together to accomplish, one of these goals.
And I think that's something people don't appreciate, right? Because we get excited for the launch of a telescope and getting the data back, but it's sort of magic happens, right? That hits your inbox. But actually making that happen and making it usable is something that requires a lot of effort. And I can tell you, when I was a student, I didn't appreciate that there were science centers that were doing work, right? You know about that.
Okay. It's enormously hard to get from the data that are on the telescope. First of all, you have to schedule the telescope and make it look at the right place at the right time. The data have to come down. They have to be turned into something useful. Those results have to be, made available to the community. Funding, hopefully, is made available as well. And then there's this sort of outreach to the community, which is one of the things that NExScI also does. We have a whole part of the Institute which is devoted to doing things like the Sagan Summer Workshop,
which we're very grateful for. And so turning to also these sort of unknown, at least to, an undergrad, can you tell us a little bit about the Carnegie, Jessica?
I'd also just like to thank you all for your work. It's a real national treasure, the work that you do. I use HST and JWST, and as a user myself, I'm incredibly grateful to just sit in my office and receive beautiful data from these amazing telescopes. I'd not heard of Carnegie until very late in my career. Andrew Carnegie was a steel baron, effectively. He was 130 years ago or so. He was, a different kind of billionaire. He invested a lot of his money into public spaces, libraries, and he set up Carnegie Institute of Washington, which is just devoted to doing science for society, basically, is how he imagined it. And so effectively, there's a large endowment that the interest of that pays for my salary and for many people's salaries. We have 3 sites. I work at the observatories. which is in Pasadena. About 100 people work there. Hubble worked there. He discovered galaxies while he was working there. But basically, we do research and nothing else. I am also supported in doing community work. I work with nonprofit School on Wheels, which serves homeless kids in LA, and the Institute supports that work too, but I basically can do what I want with my time, which is what growing up, which I thought that's what being a scientist was. So this is an institute where I feel like I am living my childhood dream. And we have postdoc programs. We have an amazing postdoc program. We have 20 postdocs who are fully funded. Carnegie runs an observatory in Chile, Las Campanas Observatory. We have two 6.5 meter telescopes, which basically we're allowed to use given time on them. A few nights a year, everybody who works at Carnegie essentially gets to use them. We also have a good hand in helping to build the Giant Magellan Telescope, which is one of the next great, hopefully, future telescopes. But yeah, it's a small place, very cozy. We do not teach students, so there are no undergrads, but we do work a lot with graduate students.
And for those of you who are visiting Pasadena, if you happen to go over to the Carnegie Observatory's building, you can actually see the diameter of the mirrors, these big circles in the parking lot. But I think it's important to note, right, that there are all of these institutions where maybe there isn't teaching, and they can look a lot of different ways. There is private philanthropy from living people. You know, we have the Flatiron Center in New York, right, the Center for Computational Astrophysics that comes from Simons. There's all kinds of other places, and also observatories that dot the country and internationally. So I think it's important just to remember that astronomy doesn't just happen in universities, but of course, that's what we're most familiar with. Stephen, why don't we turn it over to you about, you know, being at a university, but you're at this intersection of departments.
Yeah, it's been a very interesting journey because I feel fortunate in that I have been at research institutes because, of course, I was at NExScI for 5.5 years, working with Jazz, and David, and Dawn, and that was an extremely rewarding time. As Emily described, a lot of that work, other than the research, is programmatic in nature. You'll be writing documents, you'll be working with developers, and I really enjoyed that. But for me, I definitely wanted to engage more with students, and I wanted to have more flexibility. And one of the things I often think that I definitely took for granted when I was at NExScI was that I did have an umbrella of people, especially David and Chaz, who were doing the hard work to make sure that my research was funded and was allowed to go on. When I made the decision to leave NExScI and go to San Francisco State University, that's one of the things that strikes you right away. Now you're in the driver's seat. You have ultimate academic freedom, but now you are the one that is ultimately responsible for bringing in the funding that is going to feed the mouths that are within your research group. But you can build a significant research group. And one thing that's always meant a lot to me are the mentors that taught me and inspired me. And I wanted to give back to that. And I was at San Francisco State for 4 years. And then I moved to UC Riverside, which is a very research-focused university. So the teaching of the undergraduate role is fairly minimal, but we have a lot of excellent graduate students who have now gotten positions elsewhere all around the world and are part of a growing family. So that's a very rewarding part of that. But it is something that you do need to take on more responsibility in applying for grants and building up that team. You mentioned the interdisciplinary part, because I had always been in a physics and an astronomy department before UC Riverside, but I moved into an Earth and planetary science department because, as I mentioned, I was going back more the planetary route. And one other thing to be aware of in the academic environment compared to being in a research institute that I've definitely found is that in a research institute, you're often surrounded by other research scientists who are interested in, if not exactly the same thing as you, usually something very similar. And so you live within that ecosystem. Often when you're a university, you're building your own group, and the other faculty usually are quite different from yours. And that can be a feeling of isolation, but then it's up to you to take your group out to network and interact with neighboring institutions. And that's an interesting, different dynamic as well.
Thanks, Stephen. And Heather, can you give us a little bit of the perspective of how you found the academic landscape and, the universities abroad different from your experience in the US?
Yeah, I mean, I think that there are quite a few bit of similarities, but there are, and I would say the differences are probably pretty small, actually. So in particular, like thinking about the University of Warwick, maybe it's not super well known in small town US, but it's one of the top 5% ranked globally. And I think our astronomy group, if you include the PhD students, the postdocs, and the staff, we're about like 100 people. So the astronomy group is very big. And I'd say that we're actually like one of the biggest exoplanet groups in the world. So I think we have about 10 permanent staff members just in exoplanet. So we're in the UK and actually kind of in Europe in general, it seems to be, instead of having just one person who's like a token, okay, this is our cosmologist and this is our exoplanet person and this is our star formation person, you tend to be collect a few people in a particular area, and then that is what you're kind of known for. So prior to exoplanets and still today, we are known for being very good at white dwarfs. So we're one of the big hubs for that. So we'd have several staff members who work on that. And we have several staff members who work in transients. And so would be more rare that you end up in isolation, I guess, at your university. And I think it's probably potentially similar to the US in terms of like, sometimes a US institution might be home to commissioning an instrument or something, like how Penn State commissioned NUID, for example, where Warwick is the home to the PLATO Science Management Center. And PLATO is a European space mission that is going to be doing the photometric follow-up of bright targets. So similar to TESS, but higher precision, and it's going to be longer stare fields. And that's going to be launched next year. And so we have some staff scientists just working on that, but we also have a lot of people who are your traditional academics. So I lecture and I have a research group and I bring in my own funding. I would say in terms of like when you are applying for PhDs, for example, it's somewhat similar in the sense that you would have to write a personal statement or whatever, but when you apply, rather than just applying to an institute at large with a general idea that you wanted to do exoplanets, there'd be specific projects that are being offered with specific advisors, and then you would apply to those projects in particular. But then at the postdoc stage, it's pretty much the same. Also, the PhD stage, we're much faster. So if you come to the UK to do your PhD, you'll do it in 3 to 4 years, and then you will be making postdoc money instead. So that is a nice reason to do that. Or you could be like Jessica and do your PhD quickly and then jump over to the US and possibly make more money. But let's see. And then like the postdoc level, again, yeah, postdoc level is pretty similar. You would apply for positions that are being advertised and there's fellowships and stuff. And then at the lecturing level, I think it's pretty similar, except for there's not this concept of a summer salary. So in the US, you might, even if you're permanent at academia, you might have your salary guaranteed for 9 months, but then be expected to fund the other 3 months, whereas we would just be salaried throughout, I guess. And one thing I guess I could say as well, sometimes funding is specific to like being a UK citizen, but the University of Warwick is quite lucky. Well, in particular, our astronomy department is quite lucky because we had quite a large donation by an anonymous person who was a Warwick alumni. And so we have at the moment these Warwick Prize scholarships for PhD students that are available to international students. as well as fellowships that are available to people at the postdoctoral level to sort of jump in and lead their own research program. So I guess the one thing I would say is if you're thinking about possibly going abroad, like you might be eligible for funding to do it, and you might be able to get your PhD faster, or you might be able to go and do a postdoc for 3 years in Europe for a while and then come back to the US or something. So definitely just kind of keep it as an option. And so I would say when you're looking for your next position or opportunity, look globally.
No, I really appreciate that, Heather. Right. I was someone who I went to the UK for a degree after college because I thought, oh, you can do that. Which when I started college, I had no idea that was an opportunity. And I think the fact that astronomy is so international, it's definitely something to think about because there are also all of these amazing connections with different instruments, different facilities. So I want to do just sort of a speed round question before our next sort of philosophical question. And we'll get to all of your questions in a minute. And so for those of you online, a reminder that you can put your questions in the Proto channel on Slack, and we'll have those included here in the room. But sort of my speed round question is name the, top up to 3 missions or facilities that you're excited about and you think that all of the students today should know about. And if you feel like you're on the spot, Jessica, we can have someone else.
Are they future missions or current?
I'll extend it to current too. Yeah.
Okay. JWST. That's still. I'm also GMT. And also HWO. Those are the 3.
Right. And what do GMT and HWO stand for? Because I don't think we actually ever spelled them out, right?
Yeah, my bad. Sorry. I should not be spewing out jargon. GMT stands for the Giant Magellan Telescope. So the 2 telescopes that I already work with are called the Magellan Telescope, so 6.5 meter mirror ones. So the Giant Magellan Telescope is basically going to be stacking 7 of those giant mirrors together to make one big mirror. So currently, it's like the most likely way that the US will build one of the next generation, like 20 to 30 meter scale ground-based telescopes. HWO stands for Habitable Worlds Observatory, and this will be hopefully a future giant space telescope, bigger than JWST even.
So I think people should recognize the importance of the Keck telescopes for exoplanet science. There's a wide variety of instruments, growing variety of instruments that'll be doing exoplanet work. We're working on one right now called HiSpec, which will do very high resolution exoplanet spectroscopy, high resolution imaging, and even precision radio velocity. But Keck has a wide variety of instruments that you get to propose through NExScI every 6 months. So please do that. As Jessica said, JWST, it's here, it's now, it's going to keep going. Write JWST proposals as often and as many as you can. We're getting typically 25% of the time on web, but that only happens if you all write proposals. Then the third one will be the European Extremely Large Telescope, which actually has an excellent prospect of existing in the next, 5 to 7 years, and will be a remarkable telescope for exoplanet observations.
I'm going to come back to Stephen in a second because he has special slides that need bringing up. So I'm good. Yeah. So can I actually ask Emily to go next and then Heather?
Yeah, so as already mentioned, JWST is doing extremely exciting science right now. Yeah, as Chaz said, keep proposing. The more we put forward exoplanet interest proposals onto the panels, then the more time exoplanet people will get. So keep proposing. I'm also going to mention Hubble or HST because this is really only our only UV capability at this resolution, and we have to hold on to that for as long as we can until hopefully HWO comes in the future. But Hubble is still doing some extremely great science. Is still very oversubscribed. So I think that just shows that the community is still using Hubble a lot, which is awesome. And I'll also mention the Roman Space Telescope. I've obviously mentioned the 3 space telescopes that we operate, but that's okay. I can be biased. But the Roman Space Telescope that will launch next year will also be very beneficial for exoplanet science as well, especially in the microlensing community. And I think it's going to bring a lot of exciting science and is a very community-driven space telescope. So it's a little bit different to how we operate Hubble and James Webb, but I'm really excited for the launch of that.
Thanks, Emily. Heather.
Yeah, I mean, I would have to echo some of the previous comments about being excited about the ELT. I mean, that will be the first time where we have the opportunity to potentially directly probe the exoplanet atmospheres for Earth-like planets around some of the brightest M dwarfs that could potentially be in the habitable zone. And then also pick up the Habitable Worlds Observatory, because that is where we're going to be able to actually probe this for your Earth-like planet around a sun-like star. And then I would say that I'm also, again, very keen on the PLATO mission that I mentioned, because it is going to, like, it has a higher precision than TESS and is going to have a longer stare. But I think they're quite complementary, because TESS can look at many more stars, because it looks across the sky. So it's not to say that it is better than TESS, it is different, and it's coming up, and I'm excited about that. And then I'm also on the ESO Senior Science Committee that is going to be collecting ideas to see what we do after the ELT. I'm the representative for life and habitability, so I'm keen to kind of explore, okay, what do we do in exoplanets beyond ELT when we're thinking about ground-based observatories? That's the next big question.
Thanks, Heather. And so it's fun to think about what we're doing from the ground and from space. But I'm going to turn it over to Stephen for a second, who wanted a couple of slides. So
Yeah, I'll just be real quick about this because I know we're running short of time. But I just wanted to mention from the planetary science perspective that what I'm showing here are the cover arts for the two 2020-ish decadal surveys. We've got astrophysics, but we've got planetary science as well. And I just wanted to mention to you, because this is obviously an exoplanet-themed meeting that we're going into this week, and many of you, that is your primary interest. But if we could just go to the next slide. There we go. So this is the list of primary themes and questions that were identified in the planetary science decadal. And the interesting thing there, when you look through there and you see many fundamental planetary science topics, and then you get to Q12, right down the bottom, which says exoplanets, which can almost make it seem like a bit of an afterthought. It's like, oh yeah, they exist as well. But then you'll notice that it says next to it, all themes. In other words, exoplanets connects to everything. And it's so much so that it doesn't cleanly go into one of these other themes. And this is fundamental for a lot of the work that we do in exoplanets, because, for example, if you're interested in demographics, as I'm sure many of you are because you're here, then demographics is really about planet formation and what are the lessons that we learn about the way in which our solar system formed. And if you're interested in mass-radius relationships, which I know some of you probably are as well, then that's all based on our understanding of the interior of exoplanets and how that interacts with the atmosphere and evolves through time. And it's worth remembering that the only in situ data for planets we will ever have are right here in our solar system, and those in situ data are used to build our models, which we then apply to planets that mostly we can't see and infer what their surface conditions may be like. That's a significant challenge. And so insofar as we get it wrong in the solar system, we'll be catastrophically wrong for exoplanets, and we won't even know it. And that's the scary thing that sometimes keeps me up at night. So I'll go to the last slide. And because this is just related to what we were talking about, when you ask that question, what's your top 3? Obviously, I was going to put on my Venus hat and say, well, the holy trinity of Da Vinci, Veritas, and Envision. But I'll just collect those into one. What this is showing, you've got the planetary science mission timeline at the top, astrophysics mission, meaning the exoplanet missions, at the bottom. And what this is trying to show is where they approximately line up now, these launch dates. are often they're moving targets for sure, especially right now. And they're often stated as no earlier than, right? So keep that in mind. But it gives you a sense of the timeline in where you might have these things connecting to each other. For example, there's a lot of missions that we have that are going to the Jovian system, and that's studying the interior of Jupiter as well as the icy satellites, because one of the other ones I would say I'm very excited about is Europa Clipper, which was recently successfully launched. And that's going to see orbital insertion, you can see there around about 2030. And so the reason I've got dates highlighted in yellow, by the way, is because there's actually a lot of science maturation that will be happening at the beginning of the next decade, which is not far away. The orbital insertion of many of these planetary missions are closer to us now than the launch of TESS, right? So that's as far in our future as these things are in our past. So this is coming, and it's going to be profound for exoplanets. And the one I mentioned, they're approximately halfway through JWST lifetime. What that means is we're going to be learning a lot in a fundamental way about our sister planet Venus and the structure of the atmosphere, which is going to allow us to diagnose the exoplanet spectra that we're hoping to get both from transmission with JWST and emission from HWO going into the future. And that's going to be extremely important. So if you're interested in any of these sorts of things, I will tell you that the planetary science community, essentially in their decadal, they reached out a hand to the exoplanet community. And for the PIs of these missions, they want to hear from you. If you're interested, reach out to a PI and say, hey, I'm studying these kinds of exoplanets, and I think there might be a relevant science case to your mission. Believe me, they want to hear that, and they want to collaborate with you. So that's what I wanted to say about that, about the planetary science missions. And I hope that Uranus Orbiter and Probe does happen. That was ranked top in the planetary science decadal. So the astrophysics decadal was saying, Habitable Worlds Observatory. And in the meantime, the planetary science community was saying, let's go to Uranus. So that's what the planetary science community cares about. And that's going to be really important for that synergy between the two communities going forward.
Thanks, Stephen. A quick note. So we're going to run a little bit long here, and I apologize. I've noticed people talking about hope and funding, and I know for some of us in this moment, it can feel hard sometimes to feel like everything is going to work out perfectly. So Chaz, can you just comment for us on when things don't work out perfectly? Is there still hope at the end of the tunnel there?
Okay, I've founded my career on one thing, which is unfounded optimism. And the reason for that is I've been on more missions that have been canceled than ones that I've been on. Maybe it's roughly 50-50. We had a mission called the Space Interferometer mission, which was supposed to do sub-microarc second astrometry to find Earths around the nearest 50 to 100 solar-type stars. Was going great. Decadal recommendations. 2020 decadal canceled with a footnote. I spent a lot of time working on two missions called the Terrestrial Planet Finder-I interferometer, and another one, Terrestrial Planet Finder-C for coronagraph. Back in the late 90s, in the aughts, both of those went away mostly to make way for JWST. 3 cheers, I like JWST. It was canceled a number of times as well. No good mission has made it through launch that hasn't had at least 1 or 2 near-death experiences. Roman is having one right now, but in fact, in talking to the chief scientist of Roman, Jeff Kruk, he said, oh yeah, this recent near-death experience, not a problem. This is our 4th one. So, these missions, if they really are scientifically meritorious, and the mission I referred to, TPF, Terrestrial Planet Finder-Coronagraph, is basically HWO. So it's coming back and is now the top recommendation of the US decadal and now NASA's next big mission. TPFI, the TPF interferometer, was known as Darwin in the UK. It died as well because it's complicated and hard. both sides of the pond. It's now coming back as a mission called life. So the projects are enduring because the questions are important and enduring. May not happen on exactly the time scale you want. People bemoan the astrophysics budget right now. Back in the early 90s, the astrophysics budget was in steady decline. Wes Huntress was the head of SMD at the time and just got up to the AAS and said, we'd be lucky to be flat. Flat would be the new up. And in that year, two things happened. The annus mirabilis of space science, the Mars rock, and 51 Peg. And at that point, the government said, hey, this stuff's terrific. Go ahead and start things. We got Spitzer going again. We got Webb going. We got SIM going. Well, it didn't make it all the way. We got TPF going. And these things swing back up. So what we lose on the swings, we make up on the roundabouts. And you just have to keep going. The analogy I just told Stephen was, think of Wile E. Coyote running off the cliff. So long as you don't look down, you just keep moving forward.
Yeah.
So one thing to remember about the decadals, and this is so important, they're not a blueprint. They're a direction to steer the ship. Because as Ches mentioned, there were things that that were recommended in 2000 decadal, which didn't quite work out, but just in a different form. The science questions, as you said, remain, but the science also changes. When I first started exoplanets in the mid-1990s, there were reports written by NASA, things like TOPS, toward other planetary systems. And guess what? The transit method was not even mentioned, was not mentioned. They were focusing on radial velocities, microlensing, direct imaging. It's hard to believe now, but if you're following the direction that the ship is going, which is all what the decadals are doing, then you'll find your way through.
So we're just about out of time, but does anybody have any closing remarks they want to have, especially on giving folks hope? Jessica, and then the others. And if you have questions, if you want to line up, we probably have time for maybe 1 or 2 questions in the room.
I would really like to echo what Chaz said, especially about it's so hard to predict the future. Like, especially it looks very bleak. It looks very big now. It's very distressing sometimes to think about it. But it's very actually difficult to predict what's going to happen. I think you also spoke to this too. I would actually controversially maybe argue against hope. Hope is actually not what drives me. What drives me is joy in what I'm doing in the present, and also trust in myself. I think everybody in this room to get here, you've already overcome many, many hurdles in your life. It's fantastic that you are here. You're doing great by being here. And I think trusting that like whatever's going to happen in the future, like you can get through it and you will. I think sticking with trust and joy in the present for me is, yeah, I find
Cheers.
my way to do it.
Heather or Emily, was there anything you'd like to add?
I think just a note that Chaz already commented on, that JWST was cancelled more than once, and now we have this amazing mission. And so, you know, science does prevail. There is actually a lot of support for science in the Senate in the US, and so we hope that pushback and support will pull us through. But I think it's important to be optimistic but to also stay vocal when you can about these things and how important funding for science is.
Thanks.
Yeah, and I mean, I would just echo what everyone else has said, but then also that beyond just missions, like you don't necessarily know how certain life events are going to shape you. So there were times where I thought that actually my path was more shaped by my failures than my successes, because I saw it as like, oh, these are all the graduate programs I didn't get into. These are all the postdoc positions or fellowships I didn't get. These are all the faculty positions I didn't get, or these are the grants I didn't get. But actually, like, I'm very happy where I am, and I'm glad I didn't take a different path. So like, what can feel like rejection at the time can actually just be redirection. And like many of us, we don't often talk about our failures, but they're amongst all of them, and they shape us, and as much as our successes do. And we need to like recognize that it's okay to fail at things, and that that's going to happen. but also take a time to enjoy our successes. Sometimes we're often moving the goalpost. And so make sure that like when we do get that position, or we get that paper done, or we whatever, we don't immediately move the goalpost, and we actually take time to go out and celebrate and appreciate and have gratitude for, and like champion ourselves as well as those around us.
That's a lovely note to end on. Thank you so much, Heather. So I'm going to turn it over to questions and then we'll thank our speakers. So we have one here.
Hi, my name's Ashley. I'm actually a fifth-year graduate student at Louisiana State University. And I just had a question as a graduate student about to graduate. If the panelists had any advice for students that are about to graduate, about to move into job season on kind of, especially given the state of mainly the US right now, just any advice for applying for jobs and a way to kind of keep hope going, given how every day is a new day and most of the news has been kind of bad news for us right now, and just how to keep hope and advice for job applying.
Come to Europe.
Any other comments?
Can I jump in here? If that's okay. Yeah, so when I was finishing my PhD, I actually applied for a number of space industry jobs at the same time as I applied for a handful of fellowships. And the advice that was given to me that I now pass on to my own students is like focus on developing like skills in parallel. So like the things that you enjoy doing. And then focus more on like what career path would make sense for those skills that you're good at and the things that you enjoy doing. And for me, because everyone was like, well, if you don't follow astronomy, then like become a data scientist, which is a completely valid career. But for me, I was something I didn't want to do. Like that's not something I particularly enjoy doing. Some people love it, some people not so much. And the things that I enjoy doing all aligned with things that were like within the space industry. So like using like real observations, real data, and helping things like in space that weren't necessarily research. And so I ended up with a number of space industry job offers that were all based on my skill set that I learned as an astrophysics PhD student. I ended up taking a fellowship that then ultimately led to this position I have now. But it's something that I still think about and still like value, that it's actually more important to think about the different skill sets that you can work upon that you've already been working on as a PhD student and developing those in parallel, rather than focusing on like, I'm going to become this specific job title at this specific place. Like focus on the things that you enjoy doing and that you're good at.
I think you're also partly already doing it. I think asking for help is like really the thing, very, very crucial. Getting feedback on your applications, like as much feedback as you can on your applications, I found personally very helpful.
So I'll just mention that last year, Proto, we focused on this in our careers panel a little bit as well. Obviously, it was a different landscape then, but I encourage you to go back and look at the archive for some talks. We have some nice resources that we point out. Right? There are things that have been self-organized. For example, the NASA Hubble Fellowship Program, NHFP, and other fellows have something called the Amped Up program where they actually offer feedback. I think the registration for this year is closed, but for next year, you can get actually direct feedback. And I would also just say, if you felt like we were too short here with careers today and didn't talk enough about the missions, stay tuned for the rest of the Sagan Summer Workshop, because they will talk about missions in detail on the last day. Tomorrow coming up, we actually have a careers panel. We'll actually focus on alternative careers. So Emily mentioned, the space industry. We'll talk a little bit about that and others tomorrow. So talk to us while we're here, engage on Slack, and there are lots of resources. We have going to take one quick question online, which another Ashley will say for us. So if you want to speak into the microphone, we'll do our best.
Hello, thank you guys for this wonderful panel. I'm going to read a question from online that's also on the topic of career path and trajectory. So someone asks, what advice do you have for those wanting to pivot into astronomy and exoplanets from a different field, such as the tech industry?
Pivoting into astronomy. Who'd like to take that one?
Coming into exoplanets from a different field?
Yeah.
I mean, I think it's kind of what Emily had said as well. Think about your transferable skills, really. So think about like, okay, maybe any coding skills you have, or critical thinking or problem solving, working under pressure, any of those other trends, like go and look at whatever the job requirement is or the PhD requirement requires, and then say, okay, these are the specifications of the job. How do I fit it with my profile? What are my transferable skills? So I think it's the same, I think, pivoting out or pivoting in. And as Jess said, ask for help, you know, contact people, talk to them. That's also useful.
Perfect. I'm afraid that's all the time we have for today. So can everyone give a round of applause for our amazing panelists?